Good morning.
Good morning, sir.
Okay, good. So even after 5 minutes of start of class, there are only 44 students. So this is not good. In a class of 100 plus, so only 45 to 50 are attending the classes regularly. So definitely not good. Anyways, so you just remind your friends to attend the classes regularly, and let's start. And yesterday we discussed about the types of efficiencies. So in the beginning, we had learnt how to calculate the voltage, the EMF, based on the energy input, that is the chemical energy of the reactants. Based on that voltage, again in that voltage, there is a theoretical maximum voltage, or no loss voltage, or reversible open circuit voltage, and the actual voltage that we get to measure in a fuel cell. For known reasons, the actual voltage will be definitely less than the theoretical maximum voltage. Likewise, there are two efficiencies as well, the maximum possible efficiency and actual efficiency. So based on the theoretical maximum voltage, the maximum efficiency is calculated, and based on the actual voltage, the actual efficiency is calculated. To be more specific, there are different types of efficiencies as well. So intrinsic maximum efficiency, voltaic efficiency, Faraday efficiency, and overall efficiency. So intrinsic maximum efficiency, as the name itself indicates, the maximum possible efficiency based on the total energy, that is enthalpy, and the energy available to do useful work, that is Gibbs free energy. If we take the ratios of the two, we get the maximum possible efficiency, known as intrinsic maximum efficiency. So voltaic efficiency and Faraday efficiency, again the names themselves indicate the type of how the efficiency is calculated. In case of voltaic efficiency, voltage is taken into account. Ratios of voltages, the actual voltage and the maximum voltage, will give you the voltaic efficiency. Faraday efficiency, something related to charge or current, so calculated by using the current values. So the actual current and maximum possible current will give you the Faraday efficiency. If you take all the three into account, intrinsic maximum, voltaic, and Faraday, then we get overall efficiency. These are the four types of efficiencies. With respect to questions related to this topic, that is efficiencies. So there could be 1 or 2 mark quiz questions asking you to define the three different types of efficiencies, or give the equations, expressions for these efficiencies, and the terms involved, its impact, the average values, so on and so forth. Coming to the test questions, or else part B questions, it can be anywhere between 4 to 12 marks, where you will be either you will be asked to list the types of efficiencies, or you will be asked to explain the efficiencies in detail. So when it is asked to explain in detail, it may go up to 12 marks. So you should learn more information about all these efficiencies by referring to the reference material, and you should be able to answer depending upon the marks. Okay, that's about what we learnt yesterday. So today we shall look into the losses. And briefly, we touched upon the different terminologies that are used for the same concept, that is voltage difference or potential difference. So you're able to see the presentation, right? Are you guys there?
Yes, sir.
Is the presentation visible?
Yes, sir.
Yes, sir.
Okay. 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 So why so many terms or names for the same concept? So by now we have realized that this fuel cell technology is multidisciplinary. Chemists, electrochemists, electrical engineers, chemical engineers, mechanical engineers or technologists from different disciplines have a definite role to play in these fuel cells. And each of these different disciplines have their own terms to explain the same concept. Because of that reason, there are so many different names. So over voltage or over potential, but this is slightly misleading, which gives an impression that the voltage is greater than or voltage is getting enhanced, which is not the case. Actually, we are trying to represent the difference in voltage here. So over voltage, over potential, polarization, irreversibility, losses, voltage drop are the terms that are used. Okay. And what are the causes for this drop in voltage? We also discussed about the typical IV curve, which is a characteristic feature of a fuel cell. So in an operating fuel cell, either the voltage is controlled and the corresponding current is measured, or the current is controlled and the corresponding voltage is measured. Because of that, we get to plot voltage versus current, actually current density. So which is nothing but an IV curve. And this IV curve speaks about or gives information about the different types of losses. So which are these different types of losses? Four major types: activation losses, fuel crossover and internal current, ohmic losses or resistive losses, mass transport losses or concentration losses. These are the four different types of losses. So for now, I will briefly speak about all these four losses, and after that, we shall discuss each of these losses in detail. So the first loss, activation losses, are the major part of the losses, especially in fuel cells that operate at low and medium temperatures. So first type of loss, activation loss, are dominant in fuel cells that operate at low and medium temperature. So fuel cells such as AFC, PEMFC, PAFC, and DMFC. DMFC is direct methanol fuel cell. We have not discussed anything in detail about that, but that is also a fuel cell which operates at temperature close to ambient temperature. So that is from room temperature to somewhere between room temperature and 100 degrees centigrade. Okay, in these types of fuel cells, so the importance of or the effect of activation losses is more. And what is the reason for this? Part of the voltage is lost in driving the chemical reactions. So irrespective of the type of fuel cell, reactions take place at both the electrodes, anode and cathode. Part of the voltage is lost in driving these chemical reactions, which are defined as activation losses. So next is fuel crossover and internal current. In this case, the fuel that is supplied at anode is supposed to be, is meant to be consumed at anode alone. However, part of the fuel diffuses through the electrolyte and reaches cathode. So the amount of fuel that gets diffused through the electrolyte and gets consumed at cathode will not result in flow of electrons through the external circuit. So that means this quantity of fuel, even though it is consumed at cathode, it will not aid in generation of electricity. So that is considered as a loss, which is defined as fuel crossover. The second part, the internal current, the electrolyte is meant to transport ions only. Ideally, the basic role of electrolyte is to conduct ions between the electrodes. So it is not meant to conduct the electrons. However, practically, few electrons which are supposed to move through the external circuit will move through the electrolyte, which is defined as internal current. That is also considered as a loss. Until and unless the flow of electrons take place through the external circuit, we cannot make use of it as current. So because of diffusion of fuel from anode through the electrolyte to cathode, as well as flow of electrons through the electrolyte, will result in no useful current. Hence, both of these are considered as a loss. So the third type is ohmic losses. Very straightforward irreversibility or loss, which is the resistance offered by the material for the flow of electrons. So components such as electrodes, the external circuit that connects the anode with cathode, will offer some resistance for the flow of electrons. So that is defined as resistive loss or ohmic loss. At the same time, the electrolyte will also offer resistance for the flow of ions through the electrolyte. So that is also part of this ohmic loss. So that is about ohmic losses or resistive losses. The last category is, or last type is mass transport or concentration losses. The place at which the fuel and oxidant are consumed are anode and cathode respectively. So which we basically call as reactants. So because of the reactions that are taking place at the electrolyte interface, these reactants are consumed continuously. If these reactants are not refilled with the rate at which they are consumed, the concentration of these reactants will decrease at the reaction site. So the reactants, that is fuel and oxidant, are continuously consumed at the reaction site, that is the electrode-electrolyte interface. The rate at which these are consumed depends upon the rate at which the reaction takes place. If these reactants are not made available at the reaction site at the rate with which they are consumed, the concentration of these reactants will go down. Because of that, there will be some loss in voltage. Because of this change in concentration, it is termed as concentration loss. And why does this happen? This happens because of the transport of the material. So if the mass transport is improper, is not as expected, these losses happen. So that is the reason why they are also defined as mass transport losses. So this is about these four types of losses in brief. So now let's look into each of these losses in detail. So let's start with the activation losses. Okay, so to start with, what are the reasons? So caused by the slowness of the reaction taking place on electrode surface. A portion of voltage generated is lost in driving the chemical reaction that transfers electrons to the electrode. And this type of loss is highly nonlinear. Information about this type of loss can be obtained from the first zone or first part of the IV curve. To go into details, back in 1905, way before this concept of fuel cell was termed, a person by name Toffel carried out many experiments, carried out many electrochemical reactions with different reactants. So a lot of experiments were carried out which involved electrochemical reactions with numerous reactants, different reactants, different chemicals. So at that time, because of those experiments, looking at the results, so he made an observation that irrespective of the starting materials, in all these electrochemical reactions, the losses followed a particular pattern. So based on those experimental results, he plotted these activation losses which take place at the electrode electrolyte interface or the reaction site or at the electrodes. So that over voltage or activation loss is plotted against logarithmic of current density. So current being drawn per unit area of the electrode. So logarithmic of that current density on x-axis and over voltage on y-axis. When he did that, for most of the values, the curve could be approximated to a straight line. And again, in this plot on the screen, we can see two curves, one for slow reactions and the other for fast reactions. So there is lot of information that we can get from this plot. So one is, as it is indicated, for slower reactions, the ore voltage is high even at low current densities, meaning even at very low current that is being drawn from a fuel cell, the losses associated with activation are very high. So likewise, if we consider the second curve, that is for the fast reaction, so it's this. This indicates that when the reactions are faster, the losses at low current density are almost nil. So consider this region, and since this is a plot of logarithmic of current density, so this is in the order of 10, 100,000, 10,000 and 100,000. So 1, 2, 3, 4, 5 logarithmic values. So log 1 is 10, log 2 is 100. So 1000, like that. So increases in the order of 10. Up to certain current density, for the fast reactions, the ore voltages are almost negligible. Only at very high current densities, the ore voltage is visible in case of fast reactions. So that is one observation. And later, we shall try to extract more information from these plots when we try to understand, or when we learn more about these activation losses. Okay, now the ore voltage at the electrode surface followed a similar pattern in a great variety of electrochemical reactions. So this is a plot of ore voltage, activation ore voltage against log of current density, which is known as Tafel plots. And most values of ore voltage approximate to a straight line. These are some of the observations with respect to Tafel plots. Even though all these results are based on experiments, there is a possibility to express this theoretically in the form of an equation as well. So the ore voltage or activation loss V can be expressed in terms of an equation A log I by I naught. This equation is nothing but the Tafel equation. So this is what I was talking about, the Tafel equation. So delta V ACT is the activation over voltage, can be expressed in the form of an equation, that is A log I by I naught. So here I is the actual current that is drawn from the fuel cell. I naught is defined as exchange current density, and A is a constant. The same equation can also be expressed in terms of natural logarithm. In that case, so it is the small a is represented as capital A, and logarithm to the base 10 is expressed in natural logarithm. So this is another form of Toffel equation. So as mentioned here, this Toffel equation can be expressed in different forms. So this is just one another form where the logarithm to the base 10 is expressed in terms of natural logarithm. And these two terms, A and I naught, have a significant role to play in case of activation losses. We should have better understanding of these constants or these terms A and I naught. So constant A is higher for a slow chemical reaction. Okay, so according to this equation, this constant A is directly proportional to the activation loss. That means when this value of A is higher, the associated loss will also be higher because it's a direct relation. Likewise, the constant I naught is inversely proportional to activation loss. So in case of fast reactions, so the I naught value will be higher, which is an inverse relation. Because of that high value of I naught, the associated activation losses are lower. So this I naught is defined as the exchange current density. So now let's go back to this plot. So in this plot, if you fit these curves with a straight line, so this best fit line touches the x-axis at a point. So it's these points. So these values are nothing but the exchange current densities. So for slow reaction, this I naught value is small. For a fast reaction, this I naught value is large. So which is in accordance with the equation. Okay, so what does this indicate? It can also be interpreted that this is a value at which the over voltage starts to increase from zero. Okay, so until this value, the over voltage is zero. From this current density onwards, the over voltage starts to rise. So that is what the I naught speaks about. Okay, so to proceed further, this Toffel equation is valid only at values, only at current values greater than I naught, this current density. And it is called as, the I naught is called as exchange current density, and obtained from experimental results, also has a theoretical basis. And now let's try to find out more information about these constants A and I naught. For a fuel cell which operates on hydrogen as fuel, this constant A can be defined or expressed in terms of the other terms, that is RT by 2 alpha F. So F is Faraday's constant, R is universal gas constant, T is the temperature. So looking at this equation, it gives an impression that when the temperature, operating temperature of the fuel cell increases, the A increases. So if A increases, the losses associated with the activation losses will increase. So that is the impression that we get by looking at this equation. However, the effect of temperature on these two terms A and I naught, if we look at that effect, the I naught, the increase in I naught value is far more than the increase in A because of the rise in temperature. So with increasing temperature, the effect on I naught is much more than A. Because of that reason, with increasing temperature, we do not see increase in activation losses. And this alpha is known as the charge transfer coefficient, and it depends on the type of reaction and electrode material, and usually the value of alpha will be in the range of 0 to 1, and at anode, when hydrogen is used as fuel, its value is close to 0.5 for a great variety of electrode materials, and at cathode, which is known as oxygen electrode, so its value is between 0.1 and 0.5 in most of the circumstances, and these are the observations based on the experiments that are carried out. So what are we talking about? Activation losses. These activation losses can be expressed in terms of an equation known as Tafel equation. Tafel equation has two major constants, A and I naught, and we are talking about constant A, and this constant A can be further expressed in terms of an equation, that is RT by 2 alpha F. In that, the new term is alpha, which is defined as charge transfer coefficient. Its value is different at different electrode. In spite of that, its range is 0 to 1. At hydrogen electrode, its value is mostly 0.5. At oxygen electrode, its value varies between 0.1 and 0.5 in most of the circumstances. At some point, it is mentioned that the value of alpha depends on the reaction involved and the electrode material as well. However, the impact of changing electrode material is not very significant. So experimenting with different materials to get the best possible value of A will make very little impact. And also, temperature has a less impact on A. That is because the effect of temperature on I naught is much more greater than that on constant A. So increase in I naught with temperature far outweighs any increase in A. The key to reduce activation over voltage is to increase I naught as much as possible. So for now, we realize that the contributing factors to activation over voltage are constant A and I naught. Out of the two, the effect of I naught is much more than that of A. And also, by increasing the exchange current density I naught, we can definitely bring down the activation over voltage. That's what we realized looking at the equation. Now let's try to understand what is this I naught and how to increase that. So I naught is affected by several parameters other than the electrode. So now let's see and try to get better understanding of this I naught. So look at the reactions that take place at the electrodes. To start with, in an acid electrolyte fuel cell at the cathode, where oxygen is used as oxidant, this oxygen combines with the electrons that come from the external circuit and the protons that come from the through the electrolyte to form water. So this is the reaction that takes place at cathode. At zero current density, it seems that there is no activity at the electrode. So what is the zero current density? That means the fuel cell is connected to a load. It is in working condition, but the load is not drawing current from the fuel cell. So that is zero current density. No current is being drawn by the load from the fuel cell. Ideally, in that situation, the reaction should not take place. However, this reaction is continually taking place, but it's a reversible reaction. So the reaction is taking place in both the directions at the same rate. The rate of forward reaction is same as the rate of backward reaction. Because of that, the net effect is not visible. So there is a continual backward and forward movement of electrons from and to the electrolyte, even when the current is not being drawn out of the fuel cell. So the rate at which this takes place has got something to do with the current density. So higher the rate at which these two reactions, forward and backward reactions, are taking place, higher the current density. So in case of faster reactions, the rate at which the forward reaction and backward reaction take place are high. Because of that, this value of I naught will also be high. And this current density is known as the exchange current density I naught. The moment the fuel cell is turned on, this reaction starts, whether the current is being drawn out of the fuel cell by the load or not. These reactions are taking place, and these are reversible reactions. The reaction faster. So that also, because of that, the losses due to activation will be low. If current density is high, then the surface of the electrode is more active. A current in one direction is more likely to flow when the reaction is already going on rather than starting something new. So what is this? That means if you have to start the reaction, or if the reaction starts only when the current is being drawn from the load, so it can't be that fast. But if the reaction is already taking place, just directing that reaction in a required direction will definitely be faster. So I naught is crucial in controlling the performance of a fuel cell electrode. And it is very important to make this I naught or keep this I naught as high as possible. And we shall see how that can be done. So now we realize that in this Stoffel equation, the contribution of I naught is very high. So I naught plays a significant role. And as mentioned earlier in the beginning, that this Stoffel equation can be expressed in many forms. Likewise, the same equation can be expressed in terms of current as well, which is known as Butler-Volmer equation. The same Stoffel equation is expressed in terms of current instead of the activation over voltage. So this is known as Butler-Volmer equation, which is equivalent to Stoffel equation. And effect of this exchange current density can be clearly seen by plotting cell voltage versus current density for different values of I naught. So see, this is a plot of cell voltage versus current density, which is actually an IV curve. This is not a Toffel plot. This is just a general IV curve for different I naught values, for different exchange current density values. So here we can see three curves. The one at the exchange current density of 0.01 shows a drastic, a significant loss in voltage, which is nothing but this activation over voltage. So when compared to this no loss voltage of 1.2, see, it can go as low as 0.6. Almost 50% of the voltage is lost just because of this activation when the current exchange current density is low. So if you increase that current density by an order of 100, so when the exchange current density is 1, there is a slight reduction in this activation loss. So when this current density is further increased, the exchange current density is further increased to 100, which is actually milliampere per centimeter square. So you can see that until the current that is being drawn out of the fuel cell is greater than 100 milliampere per centimeter square, there is no loss at all. Until the current density, meaning the current that is being drawn out of the fuel cell, exceeds a value of 100, the voltage is equal to no loss voltage. There is no loss in voltage at all. Even after that, see, look at the magnitude of loss of voltage. It is very low. So this plot clearly signifies that by keeping the exchange current density as high as possible, it is possible to reduce the loss due to activation. And these plots are based on an assumption that the loss in a fuel cell is only because of activation loss. So with that assumption, so it is very clear that by increasing the exchange current density, the activation losses can be brought down. So the actual voltage can be obtained by taking out the loss due to activation from the no loss voltage. And all these plots are obtained by considering a value of 0.06 for the constant A. So this is about the activation loss or activation over voltage. So we shall continue with the other three losses in the next class. Don't exit now itself, just wait. So I would like to take the attendance today. See, now the count is 59. Surprisingly, the count will go high now, just because I mentioned I'm taking the attendance. I hope you guys are still there and listening to me.
Yes, sir.
So I'm just opening the spreadsheet. Give me a moment. My goodness, it is still taking time. Okay, finally, yes. Okay, what's the date today? It's 14/10. Okay, Akash, Abhipsa,
Present, sir.
Abhirup,
Present, sir.
Aditi, Aditya Anand, Aditya Anand, Aditya BS.
Yes, sir. Present, sir.
Okay, Aditya Datta, Ajay B, Ambrish, Amulya Rao,
Present, sir.
Anirudh Sharma, Anirudh Devpura, Anuj Kumar,
Present, sir.
Anuraj, Anuraj Jha, Apurva K, Arijit Banerjee, Arpit Kapil, Ashutosh Agarwal,
Yes, sir.
Sir, Pawan.
who's present.
Ashutosh present, sir.
Okay. I have not called your name yet, Pawan.
Okay, sir. Sorry.
Ashwin Sudarshan.
Yes, sir. Yes, sir.
Okay. Ayush Srivastava from Computer Science. Ayush Srivastava from EC. Basava Chetan. Bhavit Shetty.
Present, sir.
Channa Basava.
Present, sir.
Divyanshu Anand. Durga Prasad Jena. Fatima Tabassum. Geeta Shivani. Girish Gowda. Gundappa.
Present, sir.
Harini Subramaniam.
Present, sir.
Himanshu. Himanshu Kalwar. Himanshu Sharma. Rishabh Bhargava.
Present, sir.
Rishika Rai.
Present, sir.
Rishabh is present. Rishika is also present. Okay. And Harini. Harini Subramaniam. Ishita Mudaliar. Jayat.
Present, sir.
John Bosco. Kiran K. Kushagra Kumar.
Present, sir.
Kushal Gowda. Kushal Gowda. Kushal R
Present, sir.
from EC.
Yes, sir.
MG Sharath.
Yes, sir.
Rakshit Kamath.
Present, sir. Present, sir.
Mahadev. Okay. Mahadev. Mahadev R. Mahesh Basavaraj.
Present, sir.
Malika Gowda. Mir Jasir Riaz.
Sir, present, sir.
Malika is present. Okay. Mir Jasir. Mithun.
Present, sir.
Pooja N. Nabira Shivansh.
Present, sir.
Nalin Kamal. Nandini.
Present, sir.
Nisha. Nisha V. Nitya R.
Present, sir.
Purvi Seth.
Present, sir.
Pradeep Kumar. Prajwal Hiremat. Prajwal Panchangam. Pranav Patak. Apparently, Pranav was the first one to log in, but he is not there. Prasanna Reddy.
Hi, sir.
Prasanna Reddy is there. Okay. Praveen Khanna.
Present, sir.
Preksha Shetty. Prerana KS. R. Mahant.
Present, sir.
Okay. Rajashekara.
Yes, sir.
Rajashekar A.
Yes, sir. Yes.
Okay. Ronak. Ronak R.
Sir,
Ravi
present,
Krishna.
sir.
Ronak is
Present, sir.
present. Okay. Ravi Krishna.
Yes, sir. So present, sir.
Okay. Riya Sharma.
Present, sir.
Riya. Sorry.
Present, sir.
Okay, okay. Riya is present. Riza. Riza Tanej from Information Science. Rohan Akash.
Present, sir.
Rohan is present. Okay. Yes, Darshan. Yes, Ketan. Yes, Pavan.
Present, sir.
Okay. Sadashiva. Sadashiva Hebbal. Sagar Biswari.
Present, sir.
Salim.
Present, sir.
Sandesh Nayak.
Present, sir.
Santosh D. Doddamani.
Sunday. Present.
Sandesh
Hello.
Nayak is present. Okay. Santosh. Satyant Singh. Sayam Agarwal.
Yes, sir.
Shahid. Bashir Malik. Sharan C.
Present, sir.
Sheetal SP. Shreya NM. Srinath.
Present, sir.
Srinath L.
Present, sir.
Okay. Srinidhi. Srinidhi Rachappa. Shritij.
Present, sir.
Okay. Shubham Bansal.
Sir, there are few messages in the chat box. Please see
Yes,
them.
yes. Shubham Bansal. Siddharth Prasad.
Present, sir.
Sohangi. Sohangi Srivastava. Saumya from BT.
Present, sir.
Saurabh Kittur.
Present, sir.
Saurabh is present. Okay. Spurti BV. Subhash VN.
Present, sir.
Suman Saurabh. Tushar Agarwal.
Present, sir.
Tushar is present. Okay. Tushar Goyal.
Present, sir.
Okay. Ujjwal Mahendru. Ujjwal Kumar.
Present, sir.
Okay. Utkarsh. Utkarsh Kumar. Yashika Harish.
Present, sir. Present, sir.
Okay. Zainab.
Present, sir.
Okay. Okay, yeah. Thank you.
Sir, Riza is present.
Riza is present. Just a minute. Where were you, Riza?
Sir, my speakers don't work if I don't put my headphones on, and I couldn't find that.
Okay.
Sir, Aditi also
Thank you.
from
Then what were
IC.
you listening the entire
No,
class?
you can't hear me speak without my
When
headphones.
you're talking, okay.
Yeah.
Riza is present. Yeah. Who else? So Ujjwal is present. Soumya is present. Srinidhi Rachappa says she's present. Srinidhi. Okay. And who else? Did I miss any names?
Sir, Aditi from IC.
Where were you, Aditi?
Sir, same problem. I was using my phone and I think my microphone was a problem. So,
I believe you guys.
Like I was wearing the earphones, but then I don't know what happened to the microphone.
Okay. Yeah. Anybody else? Okay. Thank you.